In my last video I mentioned the use of inverse assemblers on logic analyzers and that I didn't use them very often, and I've been asked to explain and demonstrate what an inverse assembler is. In essence, they're nothing more than a small program that interprets the data that's been captured on the analyzer, and then it reverse assembles it, trying to identify instructions, memory addresses, that sort of thing. And it displays the list view on the analyzer as if though it was a reverse assembled file. It sounds a bit complicated, but it's quite simple. They come in a couple of basic types. There is either software only inverse assemblers, which is just a small add-on file to the system, or you can get a pod attachment, which is a piece of hardware that sits between the analyzer and the unit you're testing, and it does a lot of the work for the inverse assembler in terms of signal timing and capture. The one I'm showing here is the software only version, where you can mostly download the files for free. You install them onto your analyzer and then you just select them for the specific processor that you're using. So in this case, the ZIP30 uses a 6800 processor, so that's the inverse assembler I've now loaded. I've made sure that the signals are mapped appropriately, so this is dependent on what the reverse assembler files need. So firstly, the labels need to be correct for the pin sets, so this one has to be called ADDR for the address, data for the data bus, and stat for some status lines. And what these are vary depending on the processor that you're using. So you then set up the inputs to match what the inverse assembler file requires. Make sure you have the correct clock attached, and then make sure you connect the status lines, data lines and address lines to the appropriate lines on your processor. Once you've done that, you can capture some data. So if we go to the waveform view, I've got this set up. I'll just quickly show you the trigger. I've got this set up to capture at address 39E7, and if I show you that in the listing, you can see that 39E7 is at this point. This is in the listing that I've produced previously, and I've labelled the various functions now within this listing, and this particular function was identified as moving the print head to the right. So that moves the physical print head stepper driver, and it keeps track of what the current column is and that sort of thing, and determines if it needs to wrap around to the next column, etc. We'll just look at the first few lines. So we're going to capture on 39E6, that's the address at the start of this function. So if we capture on that address, so I'll set the trigger and then I'll press the key. So notice that we have now captured 39E6, and as I say, I normally just go through the code at this point, or rather the waveform at this point, looking at the code and seeing what's going on. I actually find that easier and quicker. Also, if the machine's not working properly, then you might find that the inverse assembler shows you weird settings. So the next thing is to select the list view. Now, one of the things to bear in mind with inverse assemblers is, or at least the one on this analyzer, is that when it processes the data, it actually starts at the first line on the screen, and if that's incorrect, then it will show you garbage as the inverse assembled data. So you need to make sure that you do have this correctly aligned. So if we get it to reprocess the data, you'll see that it's giving different readings depending on what it's doing. So we need to make sure that at the top of the screen we have the start of a valid instruction. So what we can see now is if we look at the code, the first line of code is to load register B with the head step count. Head step count, of course, is a RAM address, And what I've done previously is identified most of the RAM addresses and I've given them labels, so rather than using the address I've actually changed that, given them a label, and then done a find all and replace in the file. But because I want to have those labels displayed in the analyzer, what you can do is go to the symbols table, and then for each symbol that you want to use within the system, you just type in the name. You're limited to 8 characters in this analyzer, and then all you do is go through and enter the names for each address. So in this case I've just done the first 2 that we're going to be encountering, which is at address 36 and address 37, and as you can see on the screen I've used address 36, address 37, and then given them the same or similar names within the 8 character limit. And now whenever the inverse assembler encounters these 2 addresses, it will replace them with the symbol labels that I've entered, and you can enter as many of these as you want. If we now go back to the list file, you can see that it's now using those values whenever it accesses those memory locations. But as you can see, you do kind of need to know what you're looking at here before you start trying to interpret it. So if we move this off by 1 and then try to get it to reprocess, what we get is just meaningless nonsense. It's not actually what it's doing. So I don't find it particularly useful early on. You'd need to have got the machine working to a fairly good degree and be fairly confident that it's doing what you want before you can use the inverse assembler. Once you've got to that point, if it's on CPU access only that you're looking at, then it does give you quite a clear reading. But again, bear in mind, it's not going to give you a continuous reading of the entire code. It will just interpret whatever instructions have been encountered, and then it will cycle round, so you'll find that this all repeats if you're in a loop. And again, it's alright for doing basic fault finding within small areas, but I don't find it very useful when trying to figure out how the entire machine works. But as you can see, it's quite quick and easy to use once you start entering labels. We triggered on 39E6, and this is what it is decoding on the list view to display as text. As I said, once you've been through it a few times, I think it's just as easy to look at the waveform view as it is the reverse assembler, or at least when you're dealing with hardware. And of course the other disadvantage is that the inverse assembler will know nothing about the hardware. So again, it has limited use when you're looking at hardware that's not directly linked to the data bus or the address bus. But it is quite interesting to look at and to use if you're looking purely at the firmware side of things. And if we just compare that with the code that we expect, then what we're getting is load register B with the step count, which I've called head SCN for head step count. So you can see that's what should happen, and then the next instruction is load register A with the current column, which it does at 39E8. So it all works, but whether you use it or not is up to you, whichever method you find easiest. Okay, in the next video I'll get back onto how I determined where the various bits of hardware were on the ZIP30 and how they were addressed, and how I identified the various symbols and functions, start points, etc. within the firmware. If you have any more questions or want me to cover anything in more detail, then let me know.